good evening. So good to be back with you again. Tonight we're going to be talking about propagation. It's how to get signals from one place to the other. We talked a lot about receivers and transmitters and antennas last week, but all of that won't do you any good if you can't get from South Carolina to California or wherever it is that you want to talk. So that's the whole topic of propagation. And because the general class license opens up the HF bands to those of you that are technicians, the focus is going to be primarily on HF. When we get into the extra, we'll get into more of the VHF and UHF topics on propagation. So I thought this was a good way to kick it off. You have to be able to get from one place to the other and vice versa. Can you hear me now? That was Verizon's tagline in some of their past advertising. So, and an interesting sidebar, for sound waves, you need some kind of a medium for the sound to travel through, like air or water, or in this case a string. But with the radio waves, that's not the case. Radio waves don't need a medium to travel through. They just start from one place and show up in the other. In the early days, when they're trying to figure out how this worked, they were trying to come up with a substance called ether that was the medium for RF waves to travel through, but that they weren't able to prove that that existed. So that's kind of unique to RF. So again, I've included this is an updated link. ARRL has a tremendous number of resources that supplement propagation. So I'd encourage you just to look at that. And of course, the glossary is here that covers all of the hobby. So we're going to start out talking about the ionosphere. So HF propagation can happen 3 different ways. If we look at the diagram here, we've got what's called a ground wave, where signals can hug the ground and eventually get over to an antenna if it's not too far away. A space wave is when the antennas can see each other and the radio signal is actually traveling through the air. And then sky wave, which we'll be talking about most of the time here in this section, actually goes up to the ionosphere and gets refracted back down to Earth over here. So that's sky wave. So those are the 3 different ways. The sky wave is also referred to as skip or hop. So the ionosphere is the central theme of this chapter, and I came across something that I had to take a picture of and share with you all. I'll bet you didn't know that the ionosphere was just a big blue bus. It turns out that there's an ionosphere tours company in Anderson, which is where Gary happens to live here. And it looks like they're still in business. So I saw this and I had to take a picture of it. And this kind of reminds me of a story that I'll share. One time I was in church and I had to go out to the parking lot for something. So I was getting ready to go out the door, and this little 3 or 4-year-old girl looked up at me and said, where are you going? And without missing a beat, I said, well, I'm going crazy. Would you like to come along? And she, without missing a beat, looked at me and said, oh, I don't know. I'll have to ask my mom. So I hope that you won't have to ask your mom to take a ride on the ionosphere bus. So why are we interested in the ionosphere? Well, DX, that's how we get to foreign countries from wherever we are. Worked all states. So that's a very important part of our hobby. It kind of looks like there's an antenna up here, but these are our power lines. Anyone like to come along for the ride? Well, we're all here. We're going to go on the ride together. So this is all background here. It starts about 30 miles above the Earth, goes up about 300 miles. There's something called ionizing radiation. We've got ultraviolet light and X-rays that come down from the sun, and they would wreak havoc with us humans down here if it wasn't for the protection afforded by the ionosphere. So the way this works is that these rays coming from the sun have enough power where the photons can actually knock electrons loose from the air molecules within what we're calling the ionosphere. And those loose electrons can then provide current paths for signals to bounce off of. So here we're showing that radio signals are refracted by changes in electron density, and I'll have some pictures of electron density coming up in a little bit. But as the air molecules are ionized, they form layers or regions in the ionosphere that cause this bending to occur. We'll get into that in more detail. So here's more of a scale diagram. A lot of times in the different pictures that we show for clarity, they indicate that the ionosphere is some distance above the Earth, just so you can see the individual regions. I had a friend that had brought to a ham club meeting a globe, and he had some playing cards taped to it. And his point was that those playing cards kind of presented the scale of what the ionosphere really was. It's very, very close to the Earth relative to the diameter. So here we have regions. You'll see these called layers as well. Usually regions is the preferred term. But this is what happens. Here's the sun over here, and you can see that this side of the Earth is lit up. And when this side of the Earth is lit up, these are the regions that form. We've got the D layer, which is the closest to the Earth. It's the densest air molecules. Then we've got the E layer, F1 and F2. And then at night, on the side opposite the sun, on the Earth, the D and E layers disappear, and then the F1 and F2 layers combine into just the F layer. So that's what it looks like. So you've got a day side and a night side, and this affects what appears. And these are shown as nice circles. The ionosphere is a mess, okay? Things are changing continually. Regions are overlapping. They're changing in density all the time. But roughly speaking, this is true. So one thing that we won't be talking about in the general class is something called gray line, but I'll introduce the concept here. The gray line is this line right here that separates the night side from the day side. And the cool thing about gray line is if you've got a station, if you're here and somebody's down here, a lot of times there's a greatly enhanced propagation along the gray line. We'll get into more of that in the extra class, but I just wanted to introduce the concept. Here's some heights. Here we've got the space shuttle up around 250 miles, which is in the top end of the F2 layer, just to give you some idea of scale. And then over here, we've got Mount Everest. So in the peak of Mount Everest is in what's called the troposphere. And then the D layer starts about 30 miles, E layer about 70. You can see the numbers as it goes up. Commercial airlines, by the way, fly at a lot of times between 33,000 and 42,000 feet, which is 6 to 8 miles above. You can see that they'll clear Mount Everest, but they don't get to the point of being in the D layer, just for scale. I mentioned ultraviolet and X-ray radiation, ionizing radiation. It's called ionizing radiation because it will actually cause electrons to be knocked out of molecules that they hit in our ionosphere. Now there's several pool questions that talk about disturbed conditions. So anytime something sounds bad, quite often the answer is going to be something about being disturbed. And I've got a disturbed ostrich coming up that I'll show you in a little bit. Sometimes if the ionization becomes so severe, for example during a solar flare, which we'll get into, it can actually cause a radio blackout where these layers are absorbing all of the signals across all of the bands. And you'll wonder if your antenna fell down. It's very possible maybe your antenna did fall down, but it's more likely that we're in a radio blackout. These don't happen very often. They don't last very long, but they do occur. So too much radiation can be a bad thing. Now we're going to walk through the different layers. The D layer is the lowest, a little hard to see here, but you can see that it's low down. The D region is closest to the Earth, about 30 to 60 miles in altitude. And again, remember that blue text represents pool questions. We try to highlight those for you. The D region is only present when illuminated by the sun. So it's on the sun side of the Earth. It disappears at night. when no UV rays are present. Now the absorption increases in the daytime when the UV is more intense. That's the enemy of low frequency propagation. So we'll see it in a couple of different ways that 80 meters, 160, sometimes even 40, the propagation is very bad during bright sunlight, during the middle of the day. It's because of this. In the related pool question, the D region is most absorbent of signals during daylight hours below 10 megahertz. Signals may be completely absorbed. So what's below 10 megahertz? Well, that would be 80 meters, for example. That a lot of times goes completely dead during the day in 160. Quite a few pool questions related to this, and I tried to give them all to you here as we go along. Long distance communication on 40, 60, 80, and 160. It's more difficult during the day because the D region absorbs these frequencies during daylight hours. I think we said that in the previous slide, but I'm trying to give you the exact pool question wording here. So when you see it, you'll know what it is. The E region is the next one up. Our arrow was moving up the diagram here. It's 60 to 70 miles above the Earth. Develops during the day, disappears at night. It's less dense, so it lasts longer after sunset. Being higher than the D region, it has a longer hop than the D region. You can go up to 1,200 miles with a single hop via the E region. There are several very interesting and unique propagation modes related to the E region. E-skip is one, kind of a mysterious propagation mode. Meteor scatter. When meteors come into the atmosphere, there's actually hundreds of thousands of meteorites that enter the atmosphere every day. Some of these, or most of them, are about the size of a grain of sand, but when they burn up in the atmosphere, they create an ionized trail that's actually possible to bounce signals off of. That's what meteor scatter is all about. And then there's one special case. Sometimes we can have an enhanced VHF propagation near the poles, the North Pole and the South Pole. More on that to come. Now here's the F. The F winds up being an F1 and an F2 layer, the F2 being the highest, 100 to 300 miles above the Earth, up near the space shuttle. And it breaks into the two regions during the day. At night turns into a single region. And this varies with local time, season, latitude, and solar activity. So a lot of times the ionospheric propagation, there's a lot of factors that feed into it that make our communication possible. We'll get into more of those. Now here's a key, the longest single hop for the F region up to 2,400 miles. You can see that it's higher, so you'd be able to go further off of a single bounce, as versus the E layer, you wouldn't go quite as far. The F layer, you'd go a lot longer, about double. So the E layer was about 1,200 miles. The F layer is about 2,400 miles. Now the stronger the sun's illumination, the higher the F2 region. So midday, around noon, let's say, early afternoon, that's when we've been illuminating that layer for the longest period of time with the most intense sunlight. So that would tend to make the F region, or the F2 region, F1 and F2, higher in the ionosphere. Now a couple of interesting concepts here. Here we've got the sun shining down on us. And what happens is that we've got what's called a critical angle. So at some angle from your antenna, this is your transmitting site, at some angle there will be enough refraction taking place to actually bend that wave back down so that it comes to the Earth. If you shoot it at a less steep angle, there's not enough refraction and it'll actually go off into space. So we see different angles here. And different angles of incidence will cause each one of these to come down in a different place. Now a lot of you have seen the prism example, probably from your high school science classes. So white light hits a prism, and then because the density is greater in the glass or the plastic, whatever, it will separate the different frequencies of light, and it'll bend them. So here's blue to red. Blue has got the lowest frequency, and it'll bend more. And here we got a picture of actually a radio signal. We've got a radio signal coming in, and there's a difference in electron density. And here we had glass that was the change in density with light. Here we've got electron density changing in one of the ionospheric regions, and that will bend the radio wave. And you can see if it continued to bend the radio wave, it would eventually bend it back down to the Earth. We'll have some pictures of electron density coming up. I'm trying not to get too deep into the science, but I'll have all kinds of links that you can go further if you wish to. And I realize that most of you want to learn enough of this to pass your exam, probably aren't interested in becoming scientists in the area, but I'll share some information that I think will let you go a little further, if you care to. So there's another concept here called critical angle. Okay, critical angle, so for a given frequency, it's the highest takeoff angle that will return a radio wave to Earth. So we've got a shallow takeoff angle, a greater one, and greater yet. So it's the highest takeoff angle that will return a radio wave to Earth. And remember the word highest. There's two pool questions that have highest in them. And if you can remember that, it'll help you, because they're worded in a way that you want to pick something different than that.
I have a question.
Go ahead. You scared me.
How does critical angle and maximum usable frequency, it's both about taking off. One's an angle, one's a frequency, but are they related?
Well, if we look at this diagram again, all of these are referencing the same frequency. Okay, and when we get into maximum usable frequency, we're talking about frequencies that may be varying, and we'll get into that in some depth a few slides later. So they're related, but they're different. So hang on for a better explanation when we get that far. And if that doesn't clear it up, then please ask again. That's a favorite instructor trick, by the way. If any of you ever teach anything, tell somebody you're going to get to it later, and then they'll forget about it and you'll never have to answer it. But I try not to do that. A little bit more on refraction. It's the ability of the ionosphere to bend or refract radio waves, depending upon how strongly the region's gases are ionized and the radio frequency. And here we're getting into the MUF thing. The stronger the ionization, the greater the bending, and then the higher the frequency of the wave, the less it is refracted. VHF and UHF are hardly refracted at all. So here we're starting to mix the frequency of the signal we're sending along with the refraction capabilities at an individual frequency. Critical angle, definition in the context of the pool, is the highest. Notice I've bolded and italicized this, because you're going to want to pick the lowest when you read the question, guaranteed. So remember the word highest. The highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. So here we've got the picture. If the angle is too high, it'll go off into space. If it's just right, Goldilocks, porridge isn't too hot or too cold, it's just right, comes back down. Of course, anything that's lower than that will come down. Now here's something, I don't think they talk about it in our chapter. I think Kessler might have mentioned it. This is an ionogram. An ionosonde is an instrument that will shoot a signal straight up in the air, and it'll sweep the frequency. In this case, we're going to sweep from 1 to 2 to 3 megahertz all the way up to 7. And then this is height, kilometers. And by reading those radar returns, we can see what's coming back. E layer and the F2, and those two different flavors of F2, something called an ordinary and an extraordinary wave, but that's extra stuff. But I just wanted to introduce the concept of how they can figure out where these things are. More on that to come. So the ionosound is actually measuring that critical frequency. So critical angle, as we said, is the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. And I repeat that because we've got two pool questions. That's the same trick works for both of them. Critical frequency at a given incidence angle, again, the highest frequency which is refracted back to Earth. Now, in several of these examples we'll be going through coming up, there's multiple pool questions all related to the same topic. And they're all within the same group in the question pool, so you'll only get one of them. So you'll get one or the other, and maybe neither, depending upon how many other questions are in that particular group. So critical angle and critical frequency, the same trick works for both. Now here's a little bit more on electron density, another ionogram. So it's free electrons per cubic meter. I don't know who measured that, but that's what this is. And we got the D region, the E, and the F. And these regions tend to group themselves or naturally form. So at those boundaries, that's what causes the bending. And it's a different amount during the day and during the night. So you don't really need to know any of that, but I thought I might add some clarity to how they determine what the E layer and the D layer and so forth are. So refraction is the redirection of a wave as it passes from one medium into another. And in the case of radio waves, the medium that is changing is the electron density of the ionosphere as we go through the different regions. Radio waves are refracted in the ionosphere by increasing densities of free electrons. So just kind of adding a little bit more meat on those bones. And here's a little bit more technical diagram of an ionogram. And these are located all around the Earth. I've got several links that you can look into. Kessler got into it a bit. You don't need to be an ARRL member to see this, a YouTube video. And then this Digizone link and world map is interesting because it shows you all of the places in the world where these things exist. And then they put the data out on a server so that people can go and look at this stuff. You might be wondering, well, why do we have two of these color bands showing up? Well, as we're firing this radar straight up, it goes up, hits the particular layer of interest, let's call it the E layer, comes back down to Earth. But what happens when it comes down to Earth? Well, it bounces off the Earth and goes back up, forming this ghost image up here. So much more that you can learn about that. If you're interested, you don't need that to pass your general. I just wanted to share it. This is an important concept brought out in this diagram. We have what's called ground wave and sky wave propagation. Now with ground wave, the radio signals leave your antenna and they hug the ground. What's the density difference we're dealing with here? Well, we've got the air, and then the ground is a different density than the air, which causes a downward bending of the wave. The ground absorbs radio energy, so these don't go very far, maybe 30 miles. Can't talk. Depends on frequency. The lower the frequency, the farther they'll go. But suffice it to say, it doesn't go very far. I'm just going to call it 30 miles for discussion purposes. Now, the sky wave, we're showing one hop here. We're going up and coming back down again. So we can talk to somebody in this distance here, or we can talk to somebody out here at this distance. Well, what about, well, here's just two different kind of hops, different angles of incidence. So we can talk here, here, and here. But in between, where the ground wave stops, and we get to the end of the first hop, that's called the skip zone. The skip zone is a place where no radio energy is getting back down to the Earth, and normally you can't hear anything there. And I had kind of an interesting case. I was going for worked all states on multiple bands, and I could not get Georgia. I live in South Carolina, and I couldn't get Georgia on 20 meters. Okay, and the reason I couldn't get Georgia on 20 meters is because I was hopping right over Georgia when I was on 20. We finally made it work. I found somebody that was calling CQ on 20 and contacted him via email and said, I'm hearing you fine, but you're not hearing me. And what we did was we moved, it was FT8, and we moved the FT8 frequency up so that nobody was competing with us, and we were able to make the contact. And that's how I finally got worked all states on 20 meters. We just had the Virginia QSO party this past weekend. Virginia is fairly close to South Carolina, and the only band I could make any contacts on was 40 meters. 20, skipping right over them again. So that's practical applications of how some of this theory works. A little bit more on sky wave and ground wave. The concept of hops we talked about. It's possible to go up, come down, and then go back up again. So a hop is one refraction for the ionosphere. Skip, propagation by ionospheric refraction. The higher the reflecting region, the longer the hop. And I think we commented on this earlier, the approximate maximum distance along the Earth's surface covered by one hop of the F2 region is 2,500 miles. Now the F2 region is the highest region, so it's going to go the furthest. F2 region is responsible for the longest distance propagation because it's the highest ionospheric region, which I guess is what I just said. Now what about the E region? That's lower, and it's going to go about half the distance for a single hop. The approximate maximum distance along the Earth's surface covered by one hop of the E region is 1,200. So we've got 1,200 for E, about 2,500 for the F2. And then as we showed earlier, the ground wave propagation is propagation along the Earth's surface. And this is the picture that we showed before. A little bit more on this skip zone. I'm going to jump ahead one slide so we can see the diagram a little bit more clearly. Now notice how these are called rays. It might be a little bit deceiving because this kind of implies that we're shooting laser beams, very narrow beams up into the ionosphere. It's really not like a laser beam or a laser pointer. It's more like a flashlight beam. It's kind of spread out, but the greatest intensity of that signal, look at it that way, is what we're considering. So we saw that the skip zone was from where the ground wave stopped and where we came down with that first hop. And then no signal coming down in the skip zone. There's an exception to that being the case, and we're going to talk about that in a little while. And we already talked about that, ground wave, talked about that. Right. Then we have the concept of multi-hop. Here we're going up into the ionosphere, coming back down, reflecting off the Earth, then being bent back by the ionosphere and down. So here we've got a single hop, one time up and down, and then as we continue, it winds up being a multi-hop path. And it's possible for these to go all the way around the world. You can go completely around the Earth by successfully hopping from the ionosphere down, up, and down. And then we have a concept called long path and short path. And we've got a globe shown here with Senegal, Africa, that's here, and Rome, Italy, that's up here. Now the circumference of the Earth is approximately 24,900 miles, in case you were curious about that. You don't need to know it. But the short path is when we go from Senegal to Rome directly. That distance is about 2,480 miles. Well, what would happen, do you suppose, because of this multi-hop that I explained? What would happen if we had a directional antenna, beam antenna, and we reversed it 180 degrees, so we were shooting away from Rome? Well, it's possible for that to be hopping up and down all the way around the world, coming back to Rome over here. That's called long path. So short path is here. Long path is where you're going all the way around the world to the other end. Now, first of all, that's kind of a mind bender. Usually the long path is going to be weaker, and to make it happen, you have to point your antenna 180 degrees from its short path heading. And I think you had a story you shared last time, Gary, about Montserrat.
Yeah, my friend Greg Surma, K8GL, was on a little de-expedition down to Montserrat, and I worked with him and we set up a schedule so that we could maybe have a contact, I think on 20 meters, I don't remember anymore. And so the time came and I came on frequency and I called him and nothing. And on a whim, I just turned my Yagi, 4-element Yagi, 180 degrees, called him, came right back.
Yep. So it's a real thing. In some of the DX spotting sites where somebody was heard, sometimes you'll see that they'll have an L next to the indication of that spot, meaning long path. So it's a real thing.
Can I ask you about that real quick?
Sure.
Does the ocean have anything to do with that? Because I understand that the waves bounce better off water, and so like in this example in the picture, you've got a large ocean as opposed to going over the Sahara Desert or something.
Sure. Yeah, the salt water is a good reflector of radio signals, and there's something actually called a saltwater linear. I don't know if you've ever heard that term, but salt water reflects very effectively. It will actually give you much stronger signals than if you were bouncing off the ground. So it's got a little concept of gain compared to ground. So I don't know if that helps or not, but that's the fact. Another picture of long and short path, just seeing it in a different way. Most signals or most contacts are going to be via short path, but it is possible to shoot the other way, come all the way back around. All right, we talked about that. Now to make, and here's the context of the pool questions. To make a long path contact, point your antenna 180 degrees from its short path heading. And here's another mind blower. A signal may arrive both long path and short path, resulting in a slightly delayed echo. Now it takes about, a radio signal can go around the Earth 7 times in a second. So the delay is going to be about 1/7 of a second. So if you just sent a single dit in Morse code, you could possibly hear it echoed. So human perception for an echo is about 1/10 of a second or 100 milliseconds. And in this case, a 1/7 of a second is about 140 milliseconds. So it would be possible to hear a short echo. There have been some things, I'm straying off the path here for just a second. There have been reported cases of echoes coming back to people that are much, much longer than 1/7 of a second. Wikipedia has a real interesting article on that. There's 7 or 8 different theories of how that can happen. And we'll leave extraterrestrials out of it for now.
Well, I was going to say, I'm not saying it's aliens, but it's aliens.
Yeah, one of the theories is that the signals are being reflected from way out in outer space someplace. And nobody's been able to prove this, but it's a documented fact. Occasionally, people have heard these long delayed echoes, but for our purposes, this is all you need to know, what's in the blue text. Okay, see what we can remember. Go ahead and unmute to answer the question, but give us about 3 seconds delay if you would. Which ionospheric region is closest to the surface of the Earth?
D for doggy.
D for doggy, the D region, A, alpha. What is the approximate maximum distance along the Earth's surface normally covered in one hop using the F2 region? Charlie, yep. Remember, F2 is the highest, so it'll go the furthest. And here's the E region. What is the approximate maximum distance along the Earth's surface normally covered in one hop using the E region? You get a penalty of $10 because you answered too soon. But it is Bravo. All right.
He's excited.
Yeah, I know. It's like a contest. In a contest, the goal is to be as fast as you possibly can, but we have to give a little time for our people to pause. All right, why is skip propagation via the F2 region longer than that via other ionospheric regions? Charlie, thank you, because it's the highest.
Charlie.
Yes, got it. What does the critical angle mean as applied to radio wave propagation? Hope you can remember my trick.
Delta.
It is delta. It's the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. And the temptation is Charlie, but if you can remember highest, you'll have it. What is meant by the term critical frequency at a given incidence angle?
Highest frequency.
Yes, again, highest. So don't be fooled by that. Why is long distance communication on 40, 60, 80, and 160 more difficult during the day?
Charlie.
It is Charlie. The D region absorbs signals at these frequencies during daylight hours. 80 and 160 are usually worthless. Sometimes you can get through on 40. Which ionospheric region is the most absorbent of signals below 10 megahertz during daylight hours?
Delta.
Delta. They're asking the same thing in different ways, and you're only going to get a maximum of one of these. So again, it's not as bad as it sounds. How is a directional antenna pointed when making a long path contact with another station?
Charlie.
It is Charlie, 180 degrees from the station's short path heading. What is a characteristic of skywave signals arriving at your location by both short path and long path propagation?
Delta.
Delta, slightly delayed echo may be heard. Good. Now we're going to talk about Mr. Sun and more about assessing propagation. So here's the sun. He's smiling. I don't know if the sun needs sunglasses, but this one does. The sunspot cycle repeats approximately every 11 years. It goes through a period of peaks, many sunspots. What does that represent? It's the number of sunspots present at a given time. Well, what is a sunspot? I'll have a picture of that coming up. If you're looking at the sun, filtered, of course, there's dark areas, and they're really not dark. They're just lighter than the surrounding areas. And they count those number of dark areas and apply some rules to it to come up with what they call the sunspot number. So they're very useful in assessing overall solar activity, because when there's a lot of sunspots, there's a lot of ionization that is escaping the sun that ionizes our F2 and F1 and all of the layers that help us with long distance propagation. So sunspots are usually a good thing. So during this 11-year cycle, where sunspots are at a peak, that's when propagation is the very best. The more sunspots, the more ultraviolet is generated. And then higher sunspot numbers generally indicate a greater probability of good propagation at higher frequencies. Now, by higher frequencies, we're talking 20 meters, 15 meters, 10 meters, etc. And here's a picture. We've got cycle 20, 21. We're just coming out of cycle 25, so that would be over here someplace. So 25 is on the downward trend right now, but propagation is still pretty good in cycle 25. And you can kind of read this on your own. It says which bands are good for daytime, which ones are good for nighttime. And here we've got some pictures. So here's a sun that has some spots on it. They look like dark spots, but they're just less light than the area around them. And the sunspots are basically holes in the sun's surface that emit a large amount of radiation. So here's at a solar maximum. There's lots of spots. Solar minimum, you can have what's called a spotless sun. That's where you don't see any sunspots at all. And here's a closer look. You can see the approximate size of the Earth in comparison. The Earth is much smaller than the sun. So during periods of solar activity, low periods of solar activity, like no sunspots, the 15, 12, 10 meter bands are the least reliable for long distance communications. So no sunspots or low sunspots, our higher bands don't work well. Now here's an interesting fact. The 20-meter band usually supports worldwide propagation during daylight hours at any point in the solar cycle. So 20 meters is a good go-to band regardless of where we are in the sunspot cycle. Now what happens, the sun is rotating. So let's say that we've got a nice strong sunspot right here. Well, when the sun rotates, that winds up being on the back side of the sun and is no longer Earth facing. So if it's not facing the Earth, we're not getting the benefit of the radiation that comes from that sunspot. So now hopefully this one will make sense. Rotation of the sun's surface layers around its axis on a 26 to 28 day cycle causes RF propagation to vary periodically. It'll be facing the Earth, it'll rotate around behind the sun, then it'll come back around again. Of course, there's quite often many sunspots, so that causes a big variation. And I thought it was rather interesting that they can't really figure out what, if it's 26 days or 28 days. Kastler said 25 and 34. And Dave Kastler commented that the sun is just a big squishy ball of gas. So the equator of the sun can actually be rotating faster than the poles. So another mind blower, but that's because we've got a big squishy ball of gas up there. Not important for this. This one here just has to do with the sunspots rotating around, coming back again. And here's our picture again. Ionization is a good thing because it energizes our D, E, and F layers. There's some bad things that can happen from too much radiation. We'll get into those next. Solar flares, CMEs, magnetic storms. These are all disturbed conditions. Extreme high levels of ionization can actually cause radio blackouts. So
Question.
sure, go ahead.
So you have all these suns out in space. How come space is dark?
Because there's nothing lighting it up.
And it's so big.
And it's so
The
big.
sun's in it.
Yeah, well, if you think about it, the reason that you can see in the dark, let's say you shine a flashlight beam across a dark room, well, you might see that beam crossing the doorway. What you're really seeing is just the dust particles that are reflecting from that beam. You're not actually seeing the light itself, and that's very much the way space works. If there's nothing to reflect the light, it's dark. All right, so ionization, we've got good things, we've got bad things. We talked about that. Yep, extreme levels of ionization can make you think your antenna fell down. So we're going to talk about the concept of light, the speed of light, and the speed of particles. All right? So UV and X-ray radiation from a solar flare affects radio propagation on Earth in approximately 8 minutes. Another way to say that, well, this is the speed of light. It takes about 8 minutes for light to go from the sun to the Earth.
Can I tell you a fun nerd fact?
Sure.
Really quick. So, when a photon is created inside the sun, when there's the hydrogen, helium, and all the nuclear reactions going on, it takes like over 100,000 years for that photon to reach the surface of the sun, but then only 8 minutes to get to the Earth. Crazy.
Yeah, it's goofy. Solar science and solar weather is just a fascinating area. I'm going to have all kinds of links coming up for folks that want to dig deeper into this, but I'm trying to focus on what we really need for the exam. Plus give you, some of these interesting things that we can pursue, because some of it's very interesting. So X-ray and UV radiation come at us at the speed of light, 8 minutes from the sun to the Earth. Some terminology, a solar flare is also called a sudden ionospheric disturbance, or SID, not to be confused with sudden infant death syndrome. That's something different. Increased D region ionization and absorption increases of solar disturbances, much more ionization in the D region, causing it to absorb signals, radio blackout. And then another blue text here, sudden ionospheric disturbance affects lower frequencies more than higher frequencies. Something they want us to know. And these only affect the sunny side of the Earth. I guess that makes sense. So the dark side may be relatively ineffective. So if we blast this UV and X-ray radiation toward the Earth, the dark side of the Earth will be shielded. Then we have the concept of a particle. Kessler called it junk, space junk. So what happens is these particles exit the sun, come our way. It can take 15 to several, I know Gary likes to think of it as one day. It's hours rather than minutes for the stuff to come our way. So the sun gives off a stream of particles called the solar wind. That's mostly protons and electrons and different kinds of ions. It's just junk that comes from the sun, and if it winds up coming toward Earth, it can disrupt some things. So CMEs are a big one. Coronal mass injections take 15 hours to several days to reach the Earth. Charged particles from solar coronal holes disturb HF communications. So anytime something bad is happening, we're going to have disturbed HF communication. The reason I'm emphasizing that is because there's about 3 pool questions that relate to disturbed conditions. Charged particles increase ionization in the E region, and this is actually what causes the auroral displays. The northern lights we see here, normally you only see those in the higher latitudes, Canada, Minnesota, and so forth, but if enough of that energy comes into the Earth, we can see this as far south as South Carolina. So it does 2 things. It causes ionization, which results in visible light, northern lights, and they also can cause geomagnetic storms, which is a disruption of the Earth's magnetic field, or magnetosphere. We have a couple of indices that we use. We've got Solar Flux Index, or SFI. It's a measure of solar radiation at 10.7 centimeters wavelength. Now you might be wondering, well, why would we care about that if we have sunspots? Well, SFI is correlated to sunspots, and there's a page in our book, I think it's 8-8, that gives you that correlation. Well, you can't always see the sun. Let's say it's overcast, or what would be the sunspot number if we could see the sun? Maybe we were on the backside of the Earth. So that's where SFI comes in handy. We've got the K index and the A index. The K index is the short-term stability of the Earth's magnetic field measured over a 3-hour average, and there's sites spread all around the Earth that record that and then average it. 0 is quiet, 9 is an extreme storm. And these can actually be predicted. I've got a couple of links here that go to the Space Weather Prediction Center, and you can kind of see what's coming up over what's happened over the past couple of days, and they can predict what's coming our way. Now the K index, this is something that I look at almost every time I turn on my radio, because if it's low, 0, 1, 2, etc., that means the prospect of good propagation is there. If it's really high, like it has been over the past week almost, at least the past several days, propagation is not good, or potentially not good. Disturbed, good way to put it. So we've got the A index, and we saw the K index here, short-term stability, 3-hour average. Then we've got the A index, and that's on a scale of 0 to 400. I don't remember how they do the math, but it's the long-term geomagnetic field stability. So it's an average of 8 K index values. We saw that the K index was 3 hours. If you take 8 of those, that's a 24-hour period. So the A index gives you that 24-hour average for the previous 24 hours. And I don't really care what has happened. I care about what's happening right now. That's why I always look at the K index, which is the one that's happening right now, basically. And again, a link to the Space Weather Prediction Center. And here's the ostrich that I talked to you about. I spent quite a bit of time trying to find an image of something that looked disturbed. And I thought this guy looked pretty disturbed, or at least confused. All right, so what kind of solar disturbances might we experience? Well, a solar flare a large eruption of X-ray and UV energy and solar materials on the surface of the sun in flares. A flare is light, okay? The light comes at us at the speed of light, okay, 8 minutes to get from the sun to the earth. Now a coronal hole, on the other hand, the weak area in the sun's outer layer where ionized gas and charged particles, or junk as Kessler likes to call it, escapes the sun's magnetic field. This comes at us at the speed of particles. CME is related, similar to a coronal hole, in that it's an injection of large amounts of material from the corona to the surface of the sun, comes at us at the speed of particles. All these things are going to disturb our ostrich. All of these can disturb HF communications. So here's some images in some wonderful videos here on the NASA site. We won't bother to actually look at them right now for sake of time, but here's some pictures. And these videos are fascinating. I'd encourage you to go look at these if you have the time and interest to do so. So in this one here, it looks like the sun is having a baby, almost. More disturbances. Geomagnetic. So a geomagnetic disturbance is going to mess up the magnetosphere of the Earth. And here we've got a picture of the Earth and a permanent magnet here, North Pole, South Pole of a magnet. And you may remember from your grade school and junior high school science that likes attract and opposites repel. So we've got a permanent magnet here on the Earth, north and south. Well, if the particles from the sun, these charged particles from coronal holes or coronal mass ejections, are southward facing, they'll strongly couple into the Earth at the poles, which will mess up the magnetic properties of the Earth. That is a geomagnetic storm. Geomagnetic storm is a temporary disturbance in the Earth's geomagnetic field, and a geomagnetic storm degrades high latitude HF propagation. A high latitude that would be between the equator and the North Pole. Propagation may be wiped out for a period of hours to days, and that can happen. I know somebody who was all excited about getting a contest started, and at the start time of the contest, there were no signals on the air. I think that happened to you, didn't it, Gary?
Yeah.
Yeah. But it affected everybody else as well, so. More disturbances, continuing with geomagnetic. We've got auroras. Let me jump down one. Everything that we talked about in terms of bad things that happen in space weather, they cause disturbed conditions. There's one exception that's a benefit. This is that one and only benefit. A benefit of geomagnetic activity, it creates auroras that can reflect VHF signals. So we talked about the northern lights. That was light. Light doesn't really affect radio, but the same ionization that produces the light, it produces ionized gases that signals can be reflected from. So auroras are glow of gases ionized by incoming charged particles as they flow into the atmosphere, guided by the Earth's magnetic field, kind of funneled into the Earth. And then auroral propagation is strongest on 6 and 2 meters. In order for you to take advantage of that, normally you would have to turn your antenna north toward the North Pole, or if you were in the southern hemisphere, toward the South Pole. Now, I think you actually worked somebody, didn't you, Gary, with...
Yeah, it was about a year ago I made my first auroral contact on 6 meters, single sideband. I think it was a gentleman in Indiana. He was pointing his antenna to the north, I was pointing my antenna to the north, and we were able to make a two-way conversation. It sounds freaky, it sounds distorted, but you could make things out, and that's how we made the contact.
Right. Doing that on sideband is kind of rare from what I've never made a contact
From
this way.
South Carolina.
Yeah, South Carolina, a long way from, the pole. So usually you have to be using CW in order to get through that noise, but they were able to do it on sideband. So this is that one benefit that can come from otherwise disturbed conditions. And then this is kind of an oddball here because we've been talking about ionospheric effects and so forth. We're going to switch focus in this one slide for this one pool question to talk about lightning storms. So what happens during the summer? Well, we have lightning storms. So lower frequencies typically experience high levels of atmospheric noise or static. So sometimes I should say in the summer, 40 meters, the noise level might be super, super high if there's thunderstorms in the area or between you and where you want to talk. So this is kind of an oddball question that's not really in the context of the other things we've talked about, but it'll come up. All right, so a few questions now about the sun. What causes HF propagation conditions to vary periodically in a 26 to 28 day cycle? Charlie, rotation of the sun's surface layers around its axis. How does a higher sunspot number affect HF propagation?
Alpha?
Alpha, yep, it's good. Higher sunspot numbers generally indicate a greater probability of good propagation at higher frequencies. So 10 meters, 12 meters, 15 meters will become usable. Which of the following are least reliable for long-distance communication during periods of low solar activity?
Delta?
Delta, right, just the opposite of what we previously talked about, 15, 12, 10. At what point in the solar cycle does the 20-meter band usually support worldwide propagation during daylight hours?
Delta.
D delta at any point. 20 meters is very nice that way. What is the solar flux index?
Delta?
It is delta, measure of solar radiation with a wavelength of 10.7 centimeters, which happens to be 2800 megahertz. And if you can make that reading, you can correlate that to sunspots. What does the K index measure?
Bravo?
Yeah, K is the short-term stability of the Earth's geomagnetic field. And as I like to say, it's what's happening right now. What does the A index measure? Charlie, that's the long-term stability of the Earth's geomagnetic field. A index actually takes 8 of the K indexes and averages it for 24 hours. Approximately how long does it take the increased ultraviolet and X-ray radiation from a solar flare to affect radio propagation on Earth?
Charlie?
It is Charlie. We're talking about light. Ultraviolet and X-ray are light, basically, in terms of speed. It takes 8 minutes. How long does it take a coronal mass ejection to affect radio propagation on the Earth? That's actually delta, yes, 15 hours to several days. Whereas Gary shared last year, if you can think of 21 day, 24 hours, you'll be in the range, if that's a trick that will help you. What effect does a sudden ionospheric disturbance have on daytime ionospheric propagation?
Bravo?
No. Any other? Oh, yeah. You were right. I must have been talking too long. Yeah, you were wondering what's wrong with Dave. Yeah, it disrupts signals on lower frequencies more than those on higher frequencies. I know.
You get a
sudden ionospheric disruption there, I think, in my brain. What is a geomagnetic storm?
Delta?
Delta, temporary disturbance in Earth's geomagnetic field. How can a geomagnetic storm affect HF radio propagation?
Delta.
Delta degrades high latitude HF propagation. It hurts it. How is long distance radio communication usually affected by the charged particles that reach Earth from solar coronal holes? Bravo. Yep, our ostrich is disturbed. HF communication is disturbed. Anytime you see something kind of bad, something gets disturbed. How can high geomagnetic activity benefit radio communications? That was that one exception we talked about.
Alpha.
Alpha creates auroras that can reflect VHF signals.
What height are the auroras? Are they, what level are they at?
Well, there's something called the auroral oval, and that's beyond what we wanted to get into, but basically there's an oval around that comes down from the North Pole and up from the South Pole, and the lower the latitude is, the stronger the ionization is. So I don't know if that answers your question, but it can be anywhere from the area of Michigan, for example, all the way much further south than that, depending upon how strong that radiation is.
Oh, I meant like how high they are. Are they in the F layer, the E layer?
Primarily the E layer. Yep.
Okay.
So 60-ish miles. Which of the following is typical of the lower HF frequencies during the summer?
Delta.
Delta, that's our lightning crashes, high levels of atmospheric noise, or static. All right, now we're going to continue after a break. We've been going for about an hour, so this would be a perfect time to take a break. We'll finish section 8.2, which is LUF and MUF and some other fun things, and then go on to 8.3, which is sporadic effects, which is a very short section, and then I have a demo that I want to share at the end. So 5 minutes, go stretch. Okay, we're back. So we're going to continue on with more about propagation. This half of 8.2, we'll talk about assessing propagation. And there's a couple of concepts here. There's a mess of pool questions about maximum usable frequency and lowest usable frequency. And again, we're only going to get a maximum of 1 on the exam. Well, let's talk through this. This has been confusing for a lot of people, so I'm going to approach it from a couple of different ways. So you'll have a chance of getting 100% on your exam. So MUF is maximum usable frequency. So if you just kind of think about that, maximum usable frequency, what does that mean? That means if you would go higher than the maximum, you wouldn't be able to use it, which is this text here. Frequencies higher than the MUF will not be refracted enough to get back to the Earth, and they'll pass into space. So maximum usable frequency, the definition then maximum usable frequency for communication between 2 points. And this is kind of important because if I'm going from South Carolina to California, there will be a maximum usable frequency between those 2 points. And if I'm higher than that, it won't be refracted from the ionosphere. That might be, it could be a different frequency between South Carolina and London, for example. So that's why this between 2 points appears. Lowest usable frequency, if you think about that for a second, that means if you were lower than the lowest usable frequency, the signal wouldn't get through. All right, let's look at the pool context. Lowest usable frequency for communication between 2 specific points. Frequencies lower than the LUF, lowest usable frequency, will be attenuated before reaching the destination. That's not too bad so far. It's real easy to get these confused. Frequencies below the MUF and above the LUF are refracted back to the Earth. So that's the Goldilocks region there, where the porridge isn't too hot or too cold. It's going to be just right. Frequencies below the maximum and above the minimum are refracted back to Earth. Lots and lots of blue texture. I don't remember how many pool questions. It must be 7 or 8. Okay, what factors will affect the maximum usable frequency? Well, the path, distance, and location. Remember we talked that that frequency might be different if you're going to different locations around the world. Path, distance, and location. The time of day and season. Well, that makes sense because the ionosphere is more energized in the middle of the day. In any impact from solar radiation and ionospheric disturbances, all of these things can affect the MUF. So it sounds like we've got all of these coming our way. The frequency that will have the least attenuation for long-distance skip propagation is just below the maximum usable frequency. And let me do this example first. If the maximum usable frequency is 15 megahertz, pick the next lowest ham band, which would be 20 meters, or 14 megahertz. So I'm going to jump ahead now, because this is a little bit easier to see. So here we have the maximum usable frequency, and notice that it's higher at a certain time of the day. Well, what time of the day is that? Local time, noon. Well, that makes sense, right? So the optimum working frequency is below the maximum usable frequency by just a little, and above the lowest usable frequency. So I've highlighted that here. It's this line right there. So the maximum usable frequency is here, and something just a little bit lower than that is the optimum place where you want to be. If I go back, let's see if these make more sense now. Well, those we understand. So the frequency that will have the least attenuation for long-distance skip propagation is just below the maximum usable frequency. And we saw that here. Now look at this diagram. This looks really, really weird. We've got the lowest usable frequency. It's actually higher than the maximum usable frequency. Well, guess what? This band of communications that we would normally have in here, it's blocked now. So when the LUF, lowest usable frequency, is above the maximum usable frequency, there's no propagation. This would be a radio blackout. It could be caused by a solar flare, X-ray event, or geomagnetic storm. Very unusual for this to happen, but it does. If LUF exceeds MUF, propagation via ordinary skywave communication is not possible over the path. Now I added this chart a time or two ago. So let's do some maximum usable frequency examples. Let's assume that the maximum usable frequency is 10 megahertz. Okay, 10 megahertz is approximately the 30-meter band. So the signal will refract, but just barely, because we're right at the MUF. It's better to be a little bit lower than the MUF. So what if we were transmitting on 14 megahertz? That is above the maximum usable frequency, above the MUF. It'll pass into space, will not return to Earth. And we've got a sad face there. No communication there. What if we go to 7 megahertz, which is the 40-meter band? Again, the maximum usable frequency is 10. So this is below the maximum usable frequency. The signals will refract back to Earth, and we have a happy face. So I've heard from some of our past students that this has helped them put this in context. Let's do the LUF side of it now. Let's say that the lowest usable frequency is 5 megahertz. That's approximately the 60-meter band. It'll refract, but just barely, because it's right at 5. It should be a little, okay. Better to be a little higher than 5 megahertz. So what about the 80-meter band, 3.5 megahertz? Well, with the lowest usable frequency at 5, 3.5 is lower than that. So it's below the lowest usable frequency. It'll get absorbed by the ionosphere and will not return to Earth, so that's a sad face. Now what if we go above the lowest usable frequency to 7 megahertz, which is the 40-meter band? Now we're above the lowest usable frequency, and the signals can be refracted back to Earth, and we have a smiley face. So these are just some examples to further clarify the concept. Now here's something that's interesting, and I'm going to give you all kinds of ways to do this, but you only really need to know what's in the blue text here. The rest of it is for your future ham radio career. To determine the current propagation on a desired band from your station, use a network of automated receiving stations on the internet to see where your transmissions are being received. So the concept there is we're going to be sending a signal from our location, and we'll use some special techniques to see where it's being received in the world. That's one way to do this anyway. There's a whole bunch of them. You only need to know the concept here for the pool question, but for practical purposes, there's something called PSK Reporter. All of these links work, by the way. You can investigate them. There's something called the Reverse Beacon Network, which is handy, something that I use for some specific applications. WhisperNet, we talked a little bit about Whisper during the digital chapter 6, 2 weeks ago. Something called WebSDR, and this is kind of cool because any of you can do it right now, even if you don't have an HF transceiver or receiver. You can listen to the signals around the world. Once you're licensed, you can transmit and then listen to one of these remote receivers to see if you hear yourself. There's something called the Northern California DX Foundation. They have a fascinating system set up that we'll touch on a little bit. They support an international network of beacon stations. Now, what's a beacon? A beacon is a transmitter that will come on the air and transmit for a certain period of time, and your job is to see if you hear it, okay? So they transmit on 20, 15, and 10. There's 18 of these locations around the world, all manned by volunteers. And their technique is extremely interesting. At certain points of the hour, and this is all available on their website, there's actually applications that you can get, Android and Apple, that will help you identify which frequency to be listening to at which exact time. So the way this works, the transmission consists of the call sign of the beacon, sent at 22 words per minute. If you don't know Morse code, that's okay. The trick is, are you able to hear it at all? Followed by 4 1-second dashes. So call sign, and then a dash, another one, and another one. So the call sign and first dash are sent at 100 watts. The remaining dashes are sent at 10. So we start at 100, we go to 10. The second dash is at 1 watt, and then the next one is at 100 milliwatts. At the end of each 10-second transmission, which I just described, the beacon steps to the next higher band, and the sequence repeats. So this is a way that you can use their beacons and their beacon project, Internet Beacon Project, to determine where you can hear things around the world. A lot more information about it here via this link. Reverse beacon network is kind of cool because I do parks on the air and summits on the air, and sometimes there's no cell service there, and it's really important if you're doing either of those, parks on the air or summits on the air, that you wind up being able to be spotted so people know that you're there. So the reverse beacon network, if you tell the system in advance what time you expect to be operating, as soon as it hears your signal, it will automatically spot you on that network. So that's where I've used the reverse beacon network to great effect for my personal use. Now FT8, there are certain frequencies that are designated as FT8 frequencies or watering holes. I have my radio programmed so that each one of these frequencies is there. So I can very quickly skip through all of these bands, probably less than 10 seconds. If I hear nothing, then that band is definitely bad, or dead, I should say. No signals whatsoever, because there is so much activity on FT8. If there's any activity on a band, there's going to be some activity on FT8. So this is a good indication of which bands have any propagation whatsoever. And then if you want to know where that propagation is open to, Europe or South America, China, whatever, you'd have to be able to decode these signals, and the software for decoding is free. All right, some more exam questions. What does LUF stand for?
Alpha.
Alpha, the lowest usable frequency for communication between two specific points. What does MUF stand for? Bravo, the maximum usable frequency for communication between 2 points. What factor or factors affect the MUF?
Delta.
Delta, all of these choices. What usually happens to radio waves with frequencies below the lowest usable frequency? Charlie, they're attenuated before reaching the destination. No propagation. What does the ionosphere, or how does the ionosphere affect radio waves with frequencies below the MUF and above the LUF?
Alpha.
It is alpha. Okay, that's the happy zone. Below the maximum and above the minimum, refracted back to Earth. What happens to HF propagation when the LUF exceeds the MUF?
Alpha.
Alpha. Propagation via ordinary skywave communications is not possible over that path. Which frequency will have the least attenuation for long-distance skip propagation? Alpha. They've worded this kind of funny, but it didn't fool you, just below the MUF. Which of the following is a way to determine current propagation on a desired band from your station?
Alpha.
It is alpha. Use a network of automated receiving stations on the internet to see where your transmissions are being received. Good, now we're going to move into scatter modes. This is a relatively short section, and then I've got some demo material that I think you'll like. Scatter modes. Now remember we saw this earlier. It didn't have these little fuzzy things though. We have the ground wave, we've got the sky wave, and then the skip zone in between. Now what really happens is that as we cross these boundaries, there's some amount of signal that gets refracted as we cross these boundaries. It's a fairly small amount, but it results in signals being sent into the skip zone. There's also a concept, this is our transmitting site, receiving site. There's also a concept called backscatter, where a signal will come down here and actually scatter back into the skip zone. It's not very predictable, you can't count on it, but it's a real effect. In fact, I do a lot of the 1 hour CW contests, and my friend Randy, W8FN, is about 20 miles away from me in North Carolina, and we can work on 40 meters wonderfully, but on 20 meters, it's very weak and fluttery. I can barely copy him, and I'm sure it's because of some of this scatter that's going on. That might be how I worked my Georgia station on 20 meters as well. It was probably via scatter. So there's another interesting thing. Sometimes the electron clouds that form, nobody really knows why, in the E layer that can cause scatter, sometimes they'll form in an area where you don't expect. So I know one of our friends, Matt, NU4E, commented that in working a schedule with somebody once, he couldn't get them either via short path or a long path, but when he moved his beam about 20 to 30 degrees off axis, he was able to communicate. And that was probably because of the scatter communications here.
It's sometimes called crooked path.
Crooked path, there you go. Yep. Yeah, crooked path. That's a new one on me. So these scatter modes, and here we've got, these must be beam antennas because there are multiple lobes, but they go up into the E layer and form these little electron clouds. Like I said, nobody really understands why that happens, but we appreciate it when it does. So characteristics, scatter propagation allows signals to be heard in the transmitting station skip zone, too far away to be received via ground, but too near for skip. So that it lets us violate the rules that we previously shared. Backscatter reflects signals back toward the transmitter, and it helps fill in the skip zone where signals would not otherwise be heard. Well, how does this work, you might be wondering. Well, here we've got the ionosphere, and I mentioned before that it's not clean and beautiful and exactly how they show it in the pictures. It's actually kind of rough. So what happens when a signal comes up, it winds up being reflected off all different angles depending upon where it hits in this layer. So we've got signal coming straight up, but it's coming down all over the place. And that's what the concept of that scatter is. So signals tend to be weak. Only small amounts of the signal energy is scattered into the skip zone. That's why I can hear Randy so poorly on 20 meters. Signals typically have a fluttering sound. That's kind of a weird sound, but on CW you can make it out. And HF scatter signals often sound distorted. Energy is scattered into the skip zone through several different paths, which we've illustrated over here, resulting in multipath interference. But at least it might be possible to communicate. And then we've got something called NVIS, Near Vertical Incidence Skywave. Do I have a bigger picture of that? Yeah, I do here. We'll jump back then. So here's a transmitter, circled in red. So we're transmitting. We're going almost straight up. And then we come down at distances that are close to our transmitting site. So I'm going to switch to the iPad here for a second. So here's our transmitting site, and here's the point where we want to talk. So I couldn't make it this way, direct through, because I've got to talk through this mountain. But I could, via near vertical incidence skywave, come up and then back down again and fill in that hole. So that's the concept of how that works. So what is it? It's short distance, medium frequency or high frequency propagation using high elevation angles. In other words, we're shooting straight up. Well, how can we make a signal go straight up? Well, the way we can do that, I think we mentioned in the antenna chapter, you normally want to be about a quarter of a wavelength above ground to get a radiation pattern that will go out in any direction. If you go to a very low antenna, or half wave above ground, I meant to say, if you go down to maybe a quarter wavelength or less, that will direct most of the energy straight up. So that's near vertical incidence. Our angle is going almost vertical. It is going up to the ionosphere, so it's skywave, which is why it's called near vertical incident skywave. So reflections from a signal using high elevation angles scattered back to Earth over a short range around the transmitting station. Dave Kassler mentioned that he lives in a very mountainous area, and they have a network that they run in Colorado, and the only way they can do it is using NVIS.
And the military uses this for tactical communications in mountainous regions as well.
Yep, same idea, same concept. So the most effective antenna is a horizontal dipole placed close to the ground, 1/8 to a quarter wavelength high. It winds up having an omnidirectional pattern at very high angles. In other words, it's kind of shooting straight up. Some people call these cloud warmers, or worm warmers, because that's where the energy is going. Works best at 40 meters and lower. Here was the expanded picture. And some questions. What type of propagation allows signals to be heard in the transmitting station's skip zone?
Bravo.
Bravo, that's scatter. What is a characteristic of HF scatter?
Bravo again.
Yep, bravo, fluttering sound, probably very weak. What makes HF scatter signals often sound distorted?
Delta.
It is delta. Energy is scattered into the skip zone through several different paths, so there's some multi-path distortion going on. Why are HF scatter signals in the skip zone usually weak?
Alpha.
It is alpha. Only a small part of the signal energy is scattered into the skip zone. Most of it goes direct. What is near vertical incident skywave propagation?
Bravo.
It is bravo. Short distance, medium frequency or of high wave, I can't talk again, short distance MF or HF propagation at high elevation angles, pretty much straight up. Good, and some more information. There's, like I said earlier, you probably want to learn enough to get 100% on your exam, but there's some wonderful, wonderful resources that I'll share here. One is by Michael Burnett. I mentioned him way back in the beginning. He helped with some of our learning how to learn principles. And this one is, both of these books, by the way, are on Kindle at $9.99, which is very reasonable. So Understanding Ham Radio Propagation, this is a link to it. This one's a little bit more readable, more analogies and pictures, that sort of thing. This one here is a little bit more scientific. It's by the ARRL, Here to There Radio Wave Propagation. More technical, and it's a little bit newer release. Not that science changes over time, but those are both excellent. And then if you want to get into more detail, this is even deeper, but it shares aspects that we haven't talked about, all related to propagation. User's Guide to the Magnetically Connected Space Weather System. So that's a link, and you can go look at that if you want. Like I said, you might not be wanting to get into any more depth than we covered here, but I wanted to share the resources. Now here's something that every time I turn on my radio, I usually will look at this. Paul Herman's site. You've probably seen these diagrams all over the internet and QRZ.com. They've got a variation of this. I put up two pictures here, one from last time we taught this in 2025, and then one from this afternoon. And what we're seeing here, this gives us the solar flux index, the sunspot number, the A and K indexes. And then what's really helpful, there's two things that I look for. I look for a low K index, and I look at these band conditions. So let's go back a year ago, and you'll see that all of the daytime bands were good, and all of the nighttime bands were good at the frequency that where propagation would be expected to be good. So a bunch of this stuff, and like I said, every time I turn on my radio, I'll usually take a quick peek at this to see what K is doing and what bands are open. This isn't necessarily, it doesn't necessarily correlate to whether you're going to be able to talk or not, but it's a pretty good indicator of DX activity. I've had some contest results that were very encouraging when band conditions were terrible, but most of it was close-in stations. So this is Paul Herman, who came up with all of this. He's got a ton of this information on his site, the website link. He's got a glossary for understanding current conditions, which is excellent. Goes into details on these parameters and what they mean. You can find these images on qrz.com. There was a fellow here that wrote an article, VE2XIP. He was very confused about all of these terms and numbers, so he decided to write an article that explained it to a beginner. So that this is a good article. And then again, the NOAA Space Weather Prediction Center got a ton of resources on understanding all of this stuff. Okay, the next thing I'm going to do is talk about a de-expedition that I don't have in my log yet to demonstrate HF propagation prediction tools. So here's the question. How am I going to work Sable Island? This has nothing to do with passing your test, but it'll be something that you might be very interested in once you're licensed and start working DX stations. So there's an expedition currently going on. This is relatively rare, and they're on the air operating through March 31st on all bands and modes, and they actually have 5 stations that they're running. This isn't too far away, but it'll demonstrate what I'm wanting to show. So how did I do this? Okay, using qrz.com, I can look up the call sign of the de-expedition CY0S, and that'll give me the grid square and the bearing to that site. So I'm going to do that. I think I've actually got it up here somewhere. If not, I'll just go ahead and click on it. There we go. So here's qrz.com. And I already had preloaded the call sign, CY0S. qrz.com is a wonderful resource in that you can get all kinds of information. This is called the bio. And each of you will want to populate a bio. It's free. Here's a picture of the group. These are the fellows that all got together to go work the island. Just off the coast of Nova Scotia. Bunch of information about their event. And the QRZ has got a very useful tab called Detail. Then I'll come back to the iPad again. And we'll see that on the Detail page, we've got the grid square, and we've got the bearing, and the distance that all show up there. Those are all very useful to use in our propagation software. And back to the presentation again. So going to QRZ, we looked up their call sign and we were able to find their grid square, FN93WX, that identifies where they are in the world. The bearing was 55.5 degrees. I would want to know that because I'm using a hex beam for the higher bands, and I would want to point it in that direction. And I know just for my own curiosity that's about 1,300 miles away. And then what time of day? In this case, they're operating 24 hours a day, so I could look at any time of the day and try to figure out what the best time to contact them might be on a given band and time. In my case, I'd like to try them around 3 o'clock in the afternoon, which is 1900 Zulu. So here's the frequencies that they're on. And a couple of comments here. First of all, they're on basically all the bands, all of our regular ham bands. And these are the frequencies that they'll be close to. So if you wanted to work them and get them in your log, these are the frequencies to look for them. Something interesting about the FT8 frequencies, these are not the generally published FT8 frequencies. So you'd have to set up your FT8 parameters so that you would be operating on these frequencies rather than the standard ones. For example, on 20 meters, that would be 14.070, but their de-expedition for FT8 is running on 14.091. You need to set up your software this way, and they're even running radio teletype. So that's all on their website. And we're going to talk about VOACAP. VOACAP, Voice of America, what's the rest of it, Gary?
Coverage area prediction.
Okay, yeah, Voice of America Coverage Area Prediction. All right, so we're going to do that.
No, we don't see it.
That's all right, I'm bringing it up. Hang on just a sec. It's loading. Using high-speed internet available only at Gary's house.
We're screaming too much.
Yeah, we must be, did you say streaming or screaming?
And that too.
There we go. All right, now I saved some of the parameters here. There's a place where you can put in information about antennas, the mode that you're operating, the power that you're operating. So once this comes up, there is something called a cap wheel. I'm going to click that. In this magic picture, because I've already preloaded the antennas at the expedition site and at my location, so we wouldn't have to drag you through all of that. And I'm going to make the assumption that I'm going to try to work them on FT8, and I'm going to be running 100 watts from my station at home. So what are the chances that I might be able to work them, and on what bands? So let me jump ahead to one other thing first. So here's me in South Carolina. Here's Sable Island, and here's the direct path. Now what do you suppose these red dots are here? Okay, that's the long path. So if I were to reverse my antenna direction, point it in the opposite direction, maybe I could work on long path. Because they're relatively close, that won't be necessary. But I'll show you what happens if we try to do that. So here's our cap wheel being displayed. And I said that I wanted to try to work them around 3 o'clock in the afternoon, which is 1900 hours. So notice how these numbers in the middle are shifting around as I move my cursor around the wheel. So 3 o'clock in the afternoon, 1900 Zulu. Notice the scale down at the bottom. The red is 100% chance of working them. 0% means I'm not going to work them. All right, so at 3 o'clock in the afternoon, notice that on this band, if I go around here, that's like 20, 17, 15, you can see what bands they're on. Back to 3 o'clock in the afternoon. So here on 20 meters, I've got 100% chance of working them with my FT8 and 100 watts. Well, that ought to work. Okay, what about the next band? Notice the center change to 17 meters. That's 100%. Let's go to 15 meters. That's 100%. So at 3 o'clock in the afternoon, pretty good chance I could work these folks. But let's come down here, also 3 o'clock in the afternoon. And this is 60 meters. That's white. It says 0%. What about 80 meters? That's 0%. Remember we said that the D layer was highly ionized and was absorbing signals, well, these are bands where we're not going to be talking that time of day. So here's another question that can be answered from this information. What if I wanted to work them on all bands? I really wanted them on 60 meters and 80 meters. Well, let's kind of go around to a different time of the day. Now here we've got some red going on. Let me get to a time that's reasonable, like 0300. That's about 11 o'clock at night. That's a reasonable time. I could stay up that late. So if I do that, on 80 meters, I'd have a 97% chance of working them. On 60 meters, 99%. And 40 meters, 99%. So if I wanted to work Sable Island on all of these bands, I would just pick a different time of the day for doing so. So you can kind of see how this propagation tool may work. Okay, let's move to the, let's try long path. Now this is short path, the S. I'm going to click S and turn it into an L. Wow, did you see all of the red disappear? What is the best opportunity that we would have? Well, the darkest color I can see here is this one. So on 12 meters at 1400 hours, Zulu, I'd have a 25% chance of working them. Is there a question there? Guess not.
Yeah, I would think that the colors should be reversed. And a red would think it'd be green would be
It's
good
just,
and red would be bad.
yeah, it's just the way that they did it. The red is good. So I'm going to switch back to short path again. So red means hot. We got a hot signal. All right, do it that way. Maybe that'll help you. All right, so that wasn't so great. So what are we doing here? We're doing FT8, which is very sensitive mode, and 100 watts. What would happen if I switched to single sideband? Now, single sideband requires 20-30 dB more signal than FT8. So let's see what happens to our colors here if we switch from FT8 to single sideband. Give it a minute to catch up. Notice that a lot of the red went away. Let me switch back to FT8 so you can see it. Big difference. So let's go back to sideband.
Why is there like a sudden drop off after like 1 hour? It goes from 60% to 0.
Well, it's because the ionosphere is drying up. We're going into the dark side or the light side of the Earth, and those changes can be pretty sudden. So we're back to a single sideband at 100 watts, and we noticed how a lot of the reds disappeared. So Gary can run 1500 watts sideband. So let's do that. Let's go up to 1500 watts from 100. And there, a lot of our color came back. So you can see if you change some of these values, you can see what your chances are of working that distance station and what time of the day that you would need to attempt to do that. So I don't have Sable Island logged yet, so I picked this as an example just so that I would know what to do when I get back home tomorrow and see if I can work them. All right, so that's what we did. This was just a summary shot that I took of where, if I were doing FT8 and 100 watts, I'd have a, let me switch my laser thing back on here. 20 meters, I'd have a 100% chance on 20, 17, and 15. So that's how this could be used. So I just wanted to give you an example of how propagation software, propagation prediction software worked. And these are some of the things that we tried. We wanted them on all bands, well, we picked a different time in order to do that. We went to single sideband and then increased power to 1500 watts. And then we tried long path, and that was kind of dismal. And then the last thing that I wanted to introduce you to here was Tamitha Scove. She's actually a ham. She's a PhD in space weather. I'm sure that's not what her degree is called, but that's basically what it is. She's also known as the space weather woman. And her little icon here is I love SWW, Space Weather Woman. Okay. I think she's single, by the way, but I've actually met her at a couple of Hamfests. She's a fascinating, fascinating person. And she does forecasts for space weather that are very much like the forecast you hear for your local weather station at home. Find out if it's going to be cloudy today or sunny or rainy, but she does it in terms of all of these space weather parameters. And because we're doing great for time, I think we can listen to a couple minutes of her most recently published forecast.
Space weather this week is calming down from where we've been over the last couple days. We've actually been dealing with some fast solar wind from this kind of curvy coronal hole right here. This extended finger actually kind of connected us up into that polar coronal hole, which is why we likely had some faster solar wind from this coronal hole than we expected. It actually bumped us up to solar storm conditions for a short bit, despite being so small. And as we continue calming down from it, we've also gotten grazed by a mini solar storm that grazed us off to the east. Aurora photographers at high latitudes, you might have noticed a little bit of brightening in the aurora over the last 24 hours. Aurora photographers at mid latitudes, however, likely wasn't much of a show for you because it just wasn't a big enough storm to give us much. However, things are going to be changing in the next couple days. We're going to get another chance for some decent fast winds, so just hang on there. We'll talk about it more in a moment. Now, as we take a look at the bright regions, all these
Now, when she talks about the front side of the sun, that's the side of the sun that's facing the Earth. Because the sun is rotating, all of these sunspots and areas are going to rotate behind the Earth.
active regions here, we were hoping to get a decent show from them, but they've been pretty quiescent. In fact, they're likely going to rotate off to the far side of the sun without giving us much radio blackouts or much noise at all. So amateur radio operators, what you really need to be paying attention to is region 4387. This region's actually been getting us close to R1 level radio blackouts over the last 24 hours or so. You can see a couple firings, little mini solar storm launches there. We also have this region up here that's kind of firing off some little jets, as you'll watch right here in just a second. Pop, pop, pop right there. This is actually probably the most magnetically complex region of the sun right now in Earth view. And it's mainly because we've got all of these coronal arcades. You can see them kind of slinking around the sun, kind of in this V shape. Believe it or not, this is the coronal streamer belt of the sun, and it's highly tilted right now. You can even see some filaments kind of snaking around, kind of similar to where the magnetic neutral line on the sun is right now. But it's very typical to get these shapes like this because the sun rotates faster in the middle than it does at the poles, so it has a tendency to stretch everything out this way. So expect to see that again. And in fact, as we continue taking a look, we can actually see a coronal hole that's going through the same process. It's being stretched in the middle and kind of pulled out at the sides like that. This is a very common signature that we see, and it's very symmetric with the northern and southern hemispheres. But we believe it or not, this particular coronal hole, we've seen it before. This is our sun for this rotation. You can see that coronal hole as it's rotating into Earth view, and this is what the sun looked like about a month ago. Look, it's the same coronal hole. And so what's nice about that is when we get these recurring coronal holes, we can use last month as a help predict when we're going to see the fast solar wind and how strong the fast solar wind is going to be. Well, last month, believe it or not, that fast solar wind bumped us up to storm levels, even though it's the wrong polarity for this time of year. So aurora photographers, we might get a decent chance again for some aurora show, even down to mid-latitudes. Wait for the coronal hole to look about like this. Once it gets into the position right about here, that's when we saw the fast solar wind last time, and it did bump us up almost to major storm levels. So it could give us a decent show despite the fact that it's the wrong polarity. So don't ignore this one because it looks like it could be a lot of fun over the next few days. So I'm expecting that right about the 14th. And so that should keep us going for the 14th and the 15th before things calm down. And then, well, sadly, it looks like we don't have a lot of active regions rotating into Earth view over the next few days, maybe even the next week. So after this, the space weather should really begin to quiet down for a while. And
so that's a little picture of her forecast. They come out about twice a month. You can find them on our website. And get my pointer turned back on again. Here we go. So just fascinating. And I kind of like this picture too. It looks like she's holding the sun in her hands, which is funny, but I thought you might enjoy that. And hopefully you picked up a couple of things. She was talking about the rotation occurring at different rates that were kind of stretching things out. She was talking about sunspots. She was talking about coronal holes. A lot of the things that we discussed tonight make a little bit of sense now as we're listening to the forecast. There's some terminology that we didn't touch on, but all of that supplemental material that I shared will cover that if you care to get into it. So that's just supplemental, and I wanted to make you aware of it. And I think the most happy slide we have so far is this one, end of chapter 8. So we covered a lot of stuff. I hope we gave you some practical things in addition to working through all of the pool questions, and enough background and context to help you understand why the right answers were the right answers. We always try to do that. And at this point, Gary, we can go to class chat, or you can go into your discussion for next week.
Just any comments or questions from anyone tonight?
I got one today, Gary.
Sure.
As you probably, I told you before that I took my general test a couple of weeks ago. I read ahead and studied ahead and took it, and I made 100 on the test.
Wow!
I've been taking and watching the live version and going through it again, and it is amazing how much more I've picked up and learned. After I've gone through, I memorized all the answers and made 100.
Yeah.
But now I'm learning, so it's been wonderful. Thank you so much.
Oh, you bet. We've had extras that have been extras for years, I mean decades, that have come back and listened to this just to figure out what they've forgotten and what's changed. So we're getting similar comments from them too. So thank you for that comment.
Thanks, Tom. Yeah, appreciate it.
Yep.
I have a kind of a pragmatic question about, so when you're doing de-icing, are you're aiming your antenna every time? Are you, I mean, do you have like a motorized system for your, I know for like Yagis there are, but
Right.
For a loop antenna, do you have, or you can't aim it?
If the loop is rotatable, and believe it or not, you can make them rotatable if you hang them from a tall branch, then put a rope on one end and drag it around so it'll point in a different direction. You can actually do that. In my case, I've got a hex beam, but I don't have it on a rotor. It's hanging from a tree, but I have a rope on it that's called an Armstrong rotator. And you can see why. You just grab it, you move the antenna and point it where you want. I'm going to have it on a mast and rotor. I just haven't gotten that far yet. But yeah, to answer your question, you do point the antenna toward that de-expedition if you have that capability.
And for my horizontal loops, I have an 80-meter horizontal loop, and I have a 160-meter horizontal loop, and they each have different lobes of energy in different directions. Kind of random. I didn't plan for where they would be, but I can switch between one or the other and find out which one is actually better for the target that I want to go for. In fact, our friend Bill, N4IQ, I asked him years ago, what's the fastest antenna rotator? And he says, I don't use a Yagi, I have loops, I use a switch, and the switch is faster.
Yep. Yep.
And of course with those lobes, I mean, the further away the other station is, I mean, the lobes expanding out, right? So you don't need nearly as much precision.
Correct.
Yep. Yep. Good.
I have a
All right.
question.
Sure.
Here.
Steve.
Okay, we talk about critical angle, but I haven't seen anything about how do you adjust an angle other than antenna height as far as making something near vertical, you bring it down low, and it's talked about, you know, lowering antennas, but if we're looking for a critical angle, is there a way to adjust that?
Well, sort of, kind of. What I mean by that is if you're interested in working DX long distance, you would want an antenna that has a low angle of radiation. For example, a vertical or maybe a stacked Yagi, something like that, that would concentrate all of the energy at a very low angle. You can't really dial the angle up and down because you can't.
Yes, you can.
Well,
if
go ahead.
if you have stacked antennas,
Okay.
like this, and so you start out feeding them with equal lengths of coaxial cable, and that's going to bring the angle of radiation down. But if you vary the length of the coax, if you change the phasing between them, you can steer the azimuth up and down. And in fact, in Voice of America, with our curtain antennas, that's what we would do. We would steer the azimuth up and down, and also steer that's the elevation, sorry, azimuth, elevation, and go right for the target area. So it can be done electrically.
And there's another tool out there on the market called a stack match. It has the phasing elements in it that you can control from the ground. So if you have two Yagis that are stacked, you can change the relative phase angle going to each antenna to steer that angle up and down, called a stack match.
Most hams don't do it. It's very elaborate, but the big stations, they do.
Mm-hmm.
What do you use to measure the azimuth? I know obviously with where you're pointing and with the compass, that's fine, but like if your critical angle, say you're on a hill or something, I mean, do you need just a level or something?
You computer model the antennas, and the computer will tell you with the various phasings what the takeoff angle's going to be. There's no way to empirically measure it.
Yeah, it'd be very difficult because you have to be a long ways away from the antenna to really find out where that lobe is. I've often wondered if a drone a mile away going up and down might do it, but that's just a speculative thing.
In practicality, we use something called the reciprocity principle. If you're going for a DX station, you try different settings, and the setting where you can hear them the best is likely going to be the setting that they can hear you the best.
Right. And some hams will have multiple towers or multiple beams on a tower, and they'll try it at 60 feet and 80 feet and 100 feet to achieve that same thing because the vertical angle will be a little bit different on each one.
So you're running from your shack out back to the antenna, back to the shack, back to the antenna?
Well, no, you'd have coaxes that come into the shack and you just switch them in the shack. Yeah.
Okay.
All right, we're running out of time, but next week, the last chapter in the book, it's titled Safety, but I'm going to try to convince you that ham radio is not just a hobby, it's an adventure. And then after we take our intermission, we'll take a 35-question practice test together as a group. So next week, Chapter 9, Safety, and a practice test. Any other comments, Dave?
Nope, not from here. We had fun tonight.
73, y'all.
Yep.
See you next week.
Thank you.
Thank you.
Have a great week.
You too.